Section number 13 is entitled Plane Curves and Parametric Equations. Suppose that you were told that x was equal to the square root of t and y was equal to 1 minus t. And you wanted to complete, say, this table. You wanted to find out the x and the y values for given t's. That is, I'll tell you t is 0, and say 1, and t is 2, and say t is 3. So what I want to do is I want to find xy points so I can plot them. X, y. For example, when t is 0, x would be the square root of 0 because t is 0, which is 0. So when t is 0, x is 0. When t is 0, y is 1 minus t, which is 0, is 1. So we have the point 0, 1. X, comma, y. Now, t is 1. Switch, I think. I think this time x will be 0. Excuse me, x will be 1 and y will be 0. X is equal to the square root of t. But t is 1. It says so. T is 1. And the square root of 1 is 1. And y is 1 minus t, which is 1. Y is 0. 1, 0. It's right there. Now, t is 2. So x is equal to the square root of t, which is 2. So we have x, the square root of 2. And y is 1 minus t, which is 2 right now. Y is negative 1. So when x is a little bit more than 1, y is negative 1. Say right there. And when t is 3, x is the square root of whatever t is, the square root of 3. And y is 1 minus t, which is 3, negative 2. So we get the square root is 3, negative 2. Square root of 3 is a little bit more than the square root of 2, but it's still less than 2. Maybe it's right here. And it looks like we're sketching something that looks like that. It looks like we're getting something that looks like that. Can x ever be negative? That is, can I get x values out here? The answer is no. First, let's finish the table. The answer is no. Why is that? Because x is the square root of some number. Whether it's t or v or k, doesn't matter. The square root of nothing is ever negative. X cannot be negative. So we won't get anything out here. Now, we could, say, eliminate the parameter. We could eliminate t. We could eliminate t. We know that x is the square root of t and y equals 1 minus t. If I can write t using x's, then y would equal stuff that has x's in it. If I square both sides, I get t. T is x squared. When I square this, I get t. T is just x squared. So y is 1 minus x squared. Except x has to be greater than or equal to 0. Because t couldn't be negative. T cannot be negative. So it's not exactly correct to say that this top line implies x squared is t. It implies that x squared is t, but x is greater than or equal to 0. When you square both sides, you might get erroneous answers. For example, if somebody told me that x squared is equal to t, then I wouldn't reasonably assume that x is plus or minus the square root of t, which is not true. That would be erroneous. The negative is erroneous, because we know x is not negative the square root of t. They told us it wasn't. They said, no, x is positive the square root of t. And if you think about it, this graph in red is y equals 1 minus x squared. But we're going to get rid of the pieces or the points on that graph that have x less than 0. That is, bye-bye. It's not there. It's not part of it. That's problem number 1. Now, although I only asked you to find the x and y values when t was 0, 1, 2, and 3, you should realize that t could not have been negative. It could have been more than 3. It didn't have to be. Let's try one more like this. Suppose I tell you x is equal to 4 cosine square theta, and y is equal to 2 sine theta. Y is equal to 2 sine theta. And you're being asked to fill in this table. Given some thetas, which will be on the top, find the x and y values. Negative pi over 2, negative pi over 4 for theta. How about 0, pi over 4, and pi over 2. Pi divided by 4, pi divided by 2. We want to find the x and y values for those given thetas. Stuff to the left of theta, namely negative pi over 2, negative pi over 4, 0, pi over 4, and pi over 2, those are theta values. And to the right of x, I'm going to write x values. To the right of y, I'm going to write y values. Why don't we have the sine and cosine graph in front of us? And I'll just go out to pi because we're only going up to half our pi. And here's negative pi. So there's negative pi over 2. And right here is positive pi over 2. And we'll do a similar thing for the sine graph. That's pi right there. And here is negative pi. That's not true, excuse me. Here's pi, so that's pi over 2. That's negative pi over 2. Y equals cosine theta. Y equals sine theta. Or at least part of it. Now, when it comes to x, it's an even function. Whether you square cosine of x or cosine of negative x, you get the same answer. Remember, cosine of negative x was just cosine of x. And if you happen to square them, they'll still be equal. That is, when I find the answer to 4 times cosine of negative pi over 2 squared, I have the answer all to the right. I have the x value for x when theta is pi over 2. Okay. The cosine, x is 4 times the cosine, say, pi over 2. Actually, plus or minus pi over 2. It's 0. It's 0. It's 4 times 0 squared, which is 0. So x is 0 for those two. Why don't we finish up with the x's? Cosine pi over 4. X is equal to 4 times cosine squared of plus minus pi over 4. The cosine of pi over 4, that's a 45-degree angle. 1, 1, square root of 2. Both of these angles are pi over 4. The cosine is 1 over the adjacent. Since I'm squaring it, I won't write 1 over square root of 2 as square root of 2 over 2. Because when you square this 1 over square root of 2, you get 1 squared, which is 1, square root of 2 squared, which is 2, and 4 times a half is 2. So x is 2 when x is 2, then when theta is negative pi over 4 or positive pi over 4. Okay, now let's do it when x is 0. X is equal to 4 times cosine is 0 squared. For cosine is 0 is 1. So you square the 1, you get 4 times 1, or 4. Okay, so we now have all the x values for those handful of given thetas. So now let us go back and find the y values. Now, remember that the sign of negative x is negative sine x. So, 2 times the sign of a negative angle is negative 2 times the sign of the positive angle. That is, this answer here and this answer here will just differ by signs. Same with those two. They'll just differ by signs because the angle differed by signs. So let us find out y equals 2 times the sine of pi over 2. The sine of pi over 2 is 1. So you have 2 times 1, or 2. So at pi over 2 we get 2, and negative pi over 2 we're going to get negative 2. Okay, let us try pi over 4. Y is equal to 2 times the sine pi over 4. But that gives us back the same triangle. At pi over 4, sine and cosines are equal. Sine of pi over 4 equals the cosine of pi over 4. So we get 2 times the sine of pi over 4 is 1 over square root of 2, which I don't like having a square root in the bottom, so I multiply by 1. I multiply by square root of 2 over 2. 1 times square root of 2 is square root of 2. And the bottom, square root of 2 times square root of 2 is 2. So I multiply by the square root of 2 over 2. The 2's cancel out, and I get back square root of 2. For negative sine over 4, I'll get back negative square root of 2. Okay, for the last one, the angle is now 0. 2 times the sine of 0. If the sine of 0 is 0. 2 times 0 is 0. Okay, so there's my chart. And you can try to graph this using that chart. The biggest problem is from negative pi over 2 to pi over 2 is just the length of pi. It didn't even go full cycle. It didn't go 2 pi. But if we were to graph this, we can. The x values go from 0 to 4. 1, 2, 3, 4. The y values go from negative 2 to positive 2. Negative 1, negative 2, positive 1, positive 2. And square root of 2 is between 1 and 2. Maybe for argument's sake, there's square root of 2 and negative square root of 2. So we plot the first point, 0, negative 2, which is right here. And then x is 2, y is negative square root of 2, which is right here. Then we plot x is 4, y is 0. And then we plot, interesting, x is 2, y is square root of 2. It's not even a function, because for the same x value, we got back more than one y value. We failed the vertical line test. And when x is 0, we go up to 2. So, to me, it looks something like that. Now, can we eliminate the parameter t? Can we somehow get rid of t? Can we say bye-bye t? And the answer is yes. We could definitely eliminate t. And we would do that as follows. We know that we use shorthand notation. Sine squared plus cosine squared is 1. If I bring this to the other side, that is, if I take away sine squared from both sides, I get positive cosine squared is 1 minus sine squared. That is, instead of cosine squared, I can have 1 minus sine squared theta. And with the simple division of the second equation, I could have a new way of writing sine. If I divide both sides by 2, I get y over 2 with sine theta. So x is equal to 4 times 1 minus sine theta squared. Y over 2 is just another way of writing sine theta. So x is equal to 4 times 1 minus y squared over 4. If I distribute, 4 times 1 is 4, minus 4 times y squared over 4, their 4's cancel. So x is 4 minus y squared, which is a parabola. So I eliminated the parameter. I just got it to have x and y's. X is 4 minus y squared. If you try to graph x equals 4 minus y squared, you would have gotten exactly what we got. The only big difference would have been, the only big difference would be is the following. There's no reason why this couldn't have gone longer. There's no reason why that couldn't go longer. Even in the parametric case, it should have gone longer. Okay, suppose you were just asked to sketch the following. X is equal to 3t minus 1, and y is equal to 2t plus 1. You want to sketch this. You can make up a table like we just did, but I think it'll be a lot easier to get a nice graph if we eliminate the parameter. Let's get rid of t. I want to plug in x's instead of that t. So I go to the first equation. X is equal to 3t minus 1, and I solve for t. I add 1 to both sides. So again, x plus 1 is 3t. And I divide by 3. And there's t. X plus 1 over 3, or there's a new way of writing t. X plus 1 over 3. So, get 2 times x plus 1 over 3 plus 1. So it's over 3. It's 2x plus 2. This 3, the 1, I'm going to write as 3 over this 3. This is what y equals. Cleaning this up a little bit, I get y is equal to 2x plus 5 over 3. It's just a straight line. It's just a straight line. It's a straight line where m is 2/3 and the y-intercept is positive 5/3. And we can plot it with that information. I know I crossed the y-axis at 5/3, which is 1 and 2/3. So here's 1 and 2 and 3 and 4. Okay, so it crosses the y-axis right there. So that's 1 point. X is 5/3, y is 0. But the change in y is 2, positive 2. So you add 2 to the y. That means you go up 2. The change in x is 3. So you add 3 to the x and you get another point. You get 14/3, 2. 14/3 is just below 5. 14/3, 2. And there's your line. Okay, what on earth did I just do? Well, from this point, I went up 2 because that's the change in y. I went up 2, and then I went 3 to the right. Well, how do you find out the y value right here, which, by the way, is the same as the y value right there? You take the original y value, 1 and 2/3 or 5/3, and you add 2 to it. You add 2. Yeah. What is going on here? Okay, so let's try this and do it the correct way. The original point that I put down was wrong. My concept, my theory was right. I just used the wrong point. This point right here, sorry, x was 0 and y was 5/3. So, change in y, you went up 2. So you get 2 and 5/3, which is 6 and 8. 6 and 5 is 11/3, and That's the change in y. And the change in x is 3, so you add 3 and you get 3. That is the new point. 3 comma 11 thirds. It makes sense. I'm at this point, 5 thirds, and then I go up 2, because the change in y was 2. So that's what I did. I added 2 to 5 thirds. And then the x value right here is 0, and I added 3, my change in x. That's what I did here. And I got another point, 2 points, connect the dots, get a line. Or you can go back and use the equation and plot points. Okay. If you have the y-intercept and the slope, I would do it that way to get a second point. Add the change in y to the y value of a point that you have. Add the change in y to the change in x to the x value you have. One moment, please. Couple more seconds. Okay, the next problem is, suppose you know that x is equal to t cubed, and y is equal to t squared over 2. So, and you can solve for t in the first equation, or you can solve for t squared in the first equation. If I know that x is equal to t cubed, I know if you raise to the 2/3 power, you multiply those powers. And 3 times 2/3, what do you know? It's 2. So that's t squared. If you raise the right side to the 2/3 power, you have to raise the left side. The x to the 2/3 is t squared. So in the second equation, instead of t squared, I write x to the 2/3 over 2. And there it is. Y is equal to x to the 3/2 over 2. And you can plot that equation. You can plot points on this one and start to see what it's going to look like. So y is equal to x to the 2/3 plus 2. So here I would make up a table. Now, I would pick values that I know the cube root of. And I didn't mean to write 0 there, I meant to write x. The values I know the cube root of are 0 cubed, and 1 cubed, and 2 cubed, and 3 cubed, and -1 cubed, and -2 cubed, and -3 cubed. So let me just review what's going on in case you forgot how to handle things when the power is a fraction, like 2/3. If somebody asks you, for example, what is 8 to the 5/3 power? First you ask yourself, what number do you multiply by itself that number of times to get this number? Well, it isn't 1. When I multiply 1 by itself that number of times, I don't get 8. But if you multiply 2 by itself that number of times, 3 times, you get 8. So this becomes that answer 2. What do you multiply by itself 3 times to get 8? 2. Now raise 2 to the 5th power, and you get 32. Why did this work out nicely? Because I picked a number like 8. I know is a nice integer that when you multiply it by itself 3 times gives you 8. If I put 10, that wouldn't have worked. I mean, 1 times 1 times 1 was 1, 2 times 2 times 2 was 8, 9 times 3 is 27. It went past 10. Okay, so 0 to any power is 0. 0 to any power is 0. And if you want to use the rule I just said, what times itself 3 times gives you 0? 0. 0 times itself 3 times gives you 0. So then you square that answer. You square it to 0 and you get 0. Plus 2. 0 to the 2/3 plus 2 is 0 plus 2, or 2. 1 to any power, 1 to the 2/3. What do you multiply by itself 3 times to get 1? 1. 1 times 1 times 1 is not 3. It's 1. And then you square the 1 and you get 1. So 1 to the 2/3 plus 2 is 1 plus 2, it's 3. If I have an 8 here instead, what times itself 3 times gives me 8? The answer is 2. And then square the 2. That gives you 4. So you get 4 plus 2 is 6. 27 to the 2/3. What times itself 3 times give you 27? Well, we just looked at that. 3 times 3 times 3, 27. So then I get 3 to the 2nd power, which is 9. So all I calculated was this piece. Now I have to add 2. -1. What times itself 3 times gives you -1? What number, if any, when you multiply it by itself 3 times, gives you -1? The answer is -1. -1 times -1 is 1. And 1 times that I'm just writing must be what I just wrote. Okay, so -1 to the 2/3. What times itself 3 times gives you -1? -1. Now you have to square it, which gives you +1. And don't forget to add on the 2. So you get 3. Now x is -8. -8 to the 2/3. So we're going to square, so we're never going to get negative answers. What times itself 3 times gives you -8? The answer is -2. That gives you back -8. And then when we square it, we get back 4. And then we add 2 to it. -27. What times itself 3 times gives you -27? The answer is not 3, but -3. And when you square it, you get back 9. Plus 2. 11. If you notice, 9 plus 2 is 11. We got the same answer when x was 27 or -27. -8 and 8. They both gave me back 6. -1 and +1. They both gave me back 3. Whether you plug in a negative number or a positive number, you get back the same answer. I don't mean any negative number and any positive number. I mean like 5 and -5. -11 and +11. an even function. Because the cube root of 5 or negative 5, they differ by a sign. But then you square it, so the sign disappears. The cube root of negative 13, excuse me, yeah, the cube root of negative 13 and the cube root of positive 13, they differ by a sign. But when you square those two numbers that just differ by a sign, you get the same answer. You square 9 or negative 9. You square 11 or positive 11. Same answer. So let's plot some of these. 0, well, x goes all the way up to 27. Y goes up to 11. In fact, y is never negative, which will cause me to write the x-axis fairly low. Yeah, 5, 10, 15, 20, 25. Negative 5, negative 10, 15, 20, 25, negative. And x goes up to 11. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Raise this a little bit. And good old 11. 11. 9, 7, 3, 1, 2, 4, 6, 8, 10. Okay, so when x is 0, y is 2. That's right here. When x is 1, y is 3. When x is 8, y is 6. 8 is around here, it's 6. When x is 27, way to the right, it's way up to 11. And when x is negative 1, so it's symmetrical. I look at this point up here and I put it out there. I guess you're getting something that looks like that. I guess at some point the concavity changes when it goes up. Now, of course, we could have used Calc 1 to do this. In fact, let's do that. Let's use curve sketching techniques from Calc 1. The first thing is you take the derivative. You bring down the power. You make the new power 1 less, which is 2 over 3x to the third, which is undefined when x is 0. So that might be a critical point. The derivative doesn't exist. That means maybe it's a corner point, or maybe the derivative is infinite. And the y value will be, well, we actually did that, is 2. But 0 to any power is 0, and then you add 2. So this is a critical point. Now we do the same thing for the second derivative. We find the second derivative, we see where it's undefined or 0. By the way, this is never 0 because the fraction is 0 when the top is 0. But the top is 2. It's never 0. It's always 2. Okay, so we took the first derivative, we cleaned it up. Right there, we cleaned it up. We found out the x values that either make it 0 or undefined. Then we found the corresponding y values. Now we do this all over again. We bring down the power. We get negative 2 over 9. Then we make the new power 1 less. Well, this gives us negative 2 over 9x to the 4/3 power. Now this is never 0. That is, there is no possible point of inflection. So the only values that came up was 0. So we look at the intervals from negative infinity to positive infinity, except we stop at the x values that made either the first or second derivative 0, and made the first derivative undefined. It's just 0. So it goes from negative infinity to 0, and then from 0 to positive infinity, excuse me. And we want to look at their signs, the plus minus signs of y prime in these two intervals and y double prime. Well, let's look at y prime. It's 2 over 3 x to the 1/3. 2 is always positive. It's 2. It's positive 2. 3 is always positive. What's going to decide on this fraction is the sign of x to the 3rd. When x is negative, it's negative. A positive over a positive, negative. Negative to the 3rd is negative. This fraction will be negative. When x is positive, x to the 3rd will be positive. And that whole fraction is positive. Now, let's look at the second derivative. Negative 2 is always negative. 9 is always positive. Now, the cube root of x might be negative. But then we square it. It becomes positive. So, for all x, we have negative over positive times positive, which is negative. Okay, first derivative is decreasing and then increasing. At 0, we have a min. The second derivative gives you concavity. Whenever it's negative, your graph between negative infinity and 0 will be some portion of this upside down u. Same thing when x is bigger than 0. Okay, let's put this all together and graph this again. Okay, you can't forget Calc 1 because it was in the past. You didn't forget what 1 plus 1 was. Okay, so the only real point that came up was 0, 2, right there. 0, 2. And the first derivative tells me, well, first it came down, and then it went up. The second derivative gives me the flavor. Okay? Along this first path, when x is less than 0, it's part of this. I mean, if you're part of this, but you have to be on this dotted line, well, then you're this portion. That is, it really went like that. And then you're going up. And you have to be part of this. Well, you're that part. That is, you go like that. The reason the first derivative is undefined at 0 was because there's a corner point. And there's your graph. Standard Calc 1 stuff. Take the derivative, see where it equals 0 or undefined. Find the corresponding y values for those x's that made the first derivative 0 undefined. Take the second derivative, find out where it equals 0, find the corresponding y value. Okay, let's try another one. Suppose you're told that x is equal to e to the negative t, and y is equal to e to the 3t. This first line, e to the negative t is 1 over e to the t. So we have this. Now remember that e to the 3t is e to the t cubed. Now if two quantities are equal, like x and 1 over e to the t, their reciprocals must be equal. Remember, this is x over 1. Their reciprocals are equal. So y is equal to e to the t, which is this, cubed. 1 over x cubed. So we eliminated the parameter. And I guess we should also be looking to see if there's any restriction on t. Because before we had that t had to be positive, so we got something like x was equal to y squared, but y had to be positive or something like that. So we have, now t can be anything. You can raise e to any power, you can raise e to any power and then cube it. So there's no restriction on t, so hence there's no restrictions on x or y's. And we want to graph this. Calc 1. How do you graph 1 over x cubed? Now I had to graph 1 over x, and 1 over x squared. Oh, my goodness, this is 1 over x cubed. Well, the first thing you do is realize this can be written as that. Then you take the derivative. It's negative 3x to the negative 4, which is negative 3 over x to the 4th, which is undefined at x equals 0. Which is okay anyway because the domain is x is not 0. You can't divide by 0, and that happens when x is 0. Okay, so there is no y value. There is no y value for x equals 0. Okay. Let's look at the second derivative. I would take it from here. It is 12x to the negative 5, which is 12 over x to the 5. Okay. And that's never 0. So what we do is we go from negative infinity to positive infinity. We have to stop off at 0, and any other x value that either made the first derivative undefined or 0. Same for the second derivative. And that only happened at 0 anyways. So we go from negative infinity to 0, 0 to infinity. And we look at the sign of y prime and this plus minus sign of y double prime in each of these intervals. Well, y prime is negative 3 over x to the 4th. Now notice we're skipping 0 anyways. So, I mean, here x is negative, here x is positive. You raise it to the 4th power, it's always going to be positive. And the top is always going to be negative. So it's always negative. It's going down, and then it goes down some more. Y double prime. Well, the numerator is always positive. It's 12. And if you raise a positive number to the 5th, it's positive. If you raise a negative number to the 5th, it's negative. And all these numbers are negative. Okay, so that means it's like this part of that, and when it's a positive concavity, it's part of that. And we have a vertical asymptote at 0. We have a vertical asymptote at 0. Because that's the value that made the bottom 0, but didn't make the top 0. So now we need to talk about that. So we have vertical asymptote at x equals 0. So we need to look at the limit as x goes from 0 from below of 1 over x cubed, which is going to be, if you're below 0 and you get cubed, you'll be negative. So you have 1 over a really, really large negative number. Well, positive 1 over a negative is negative, and 1 over really large is 0. So it's getting closer to 0. And the limit as x goes to 0 plus, same argument. The top and the bottom are positive. 1 over large cubed is 1 over large, which is 0. And since it's a rational function, we have to look at the limits at infinity. Oh, what am I saying? 0 cubed is close to 0, but negative. 1 divided by close to 0 is infinity. Sorry. Very sorry. So it's going to negative infinity. 1 over if x is a little bit more than 0, it'll be positive. Because 1 is positive, more than 0 cubed is positive. It's still 1 over really small, which is infinity. Positive infinity, sorry. 1 over large cubed is 1 over large. That is positive 1 over positive large. It's positive. And if x gets bigger and bigger and bigger, you get closer to 0. But always from above. You'll always be a little bit more than 0. Because this is always positive, this is always positive. You have one pizza pie, and more people come in to share in that pie. More and more come in. Eventually, people are going to get almost 0, but they'll get something. It'll be positive. Take a pizza pie and divide it into a billion pieces, you get something. Okay, limit as x goes to negative infinity of 1 over x cubed. The top will be positive, negative, cubed is negative, and 1 over really, really large, because when you cube a negative number, you get a large negative number. It already took care of the fact that it's negative and 1 over large is 0. So you're getting closer to the 0, but through negative numbers. Okay, now we can graph this. Let us do so. We know that we have a vertical asymptote at 0. So it's hard to draw a vertical asymptote right above the y-axis, but there it is in red. Y, x. And we know that when x is a little bit less than 0, you're at negative infinity, which is right here. When x is a little bit more than 0, you're at positive infinity. Go a little bit to the right of 0, and I go up to positive infinity. When x goes all the way to the right, to positive infinity, you get closer and closer to 0, but from above. So the record, if you went below, then it would go something like that. It would go something like that. Notice at the far right, I'm getting closer and closer to 0, but through positive numbers. But we don't have that. And so let me erase it over here. What happens at negative infinity? It goes to 0, but from below. I'm a little bit below 0. And to the right of 0, I'm going down, and I'm a portion of this. That is, I'm that portion. Going like that. To the left of infinity, to the left of 0, I'm also going down like that, and I'm a portion of this. I'm the right portion. Goes like that. And there's the graph. Looks very similar to 1 over x squared. Or 1 over x, excuse me. Okay, let's see. Sure. That completes the section on parametric equations and plain curves.